Go ahead and start recording. So today we want to finish up with inverses, transpose, and then we want to get into LU factorization. So we finished up with how to find an inverse. And unfortunately with linear algebra, a lot of these problems, they do take a long time to work out. So hopefully that'll be good, since I don't think it's too much material-wise to cover today. We'll have time for examples. And what we want to start with is why inverses are useful. So it gives us another technique. This technique of, actually we've got, excuse me, elementary matrices. So maybe we do have a bit to cover today, but elementary matrices aren't too bad. Okay, so we wanted to start off with inverses and how we can use inverses to solve a system. Solve a system, I'll say the system of linear equations by inverses. And this might be a lot of these, right? A lot of these computational methods are ways you can kind of program a computer to solve these. If you had to program a computer to do all these row operations, it might actually be kind of hard to, especially for a generic matrix, to get it to recognize which row operations to do. But most programming packages already have matrix math installed. So if you needed to solve a system of linear equations, so for example, let's have x plus z equals 1, x minus y plus z equals 3, x plus y minus z equals 2. So if we wanted to program a computer to solve something like this, it's going to be easiest, in my opinion at least, probably to write it in matrix form. So we saw yesterday how we can pull out the coefficient matrix and write the system of equations as the coefficient matrix times the variable column vector, and we are looking for a solution. We are looking for the values in the variable vector that will satisfy this equation. So let's call this matrix A. And typically when we have our variable vector, we'll call it capital X. So capital X, sometimes we'll write it as x1, x2, x3 with just subscripts for the indices, or we can write it as x, y, z. But capital X in general is our variable vector. And then this guy, let's call B for our constants. So what we're doing is we're trying to solve the equation AX equals B. And now our tool is, if we can find an inverse of A, we can multiply both sides by A inverse on the left. And be careful, right? Our multiplication is non-commutative. So if I multiply on the left by a matrix on one side of the equation, I have to multiply by the left by that same matrix on the right side of the equation. So we're multiplying both sides of the equation by A inverse on the left. And when we simplify this, A times A inverse is going to give us I, the identity matrix, times X, is equal to A inverse of B. And the identity matrix times X is simply going to give us X. So in other words, our x, y, and z can be found fairly easily if we know the inverse of the matrix. And again, a computer system, as soon as we define our system of equations as a matrix, a computer system can easily find the inverse for us, and then it can also easily do the product here, and then it'll give us the vector of solutions. So let's go ahead and work that out. Let's compute the inverse real quick. So we had, make sure I'm on screen here, 1, 0, 1, 1 minus 1, 1, and 1, 1 minus 1. And so what we want to do to create an inverse, we are going to put the identity matrix joined to the right. And now we are simply going to perform row operations on the left until we get the identity on the left side. So let's go ahead and do minus row 1 plus row 2. And sorry, let's do it down here. So 1, 0, 1, we'll have minus row 1 plus row 2, and minus row 1 plus row 3 to get rid of those leading ones below the top column. So we'll still have a minus 1 here, and then here we will have a 0. We will have a 1 here, and then a minus 2 here. Let's perform those same operations on the identity. So top row is not going to change. Minus row 1 plus row 2, minus 1, 1, 0, and then minus 1, 0, 1. So closer. Go ahead and multiply row 2 by a negative. So now row 2 is nice. Let's go ahead and finish off row 3 and then do minus row 2 plus row 3. Or we could do that row 2 plus row 3 and then do the minus. Whichever order you like, just be careful with the arithmetic. So we will have a 0 here, a minus 2 here, and then we're just adding these two. And then our last step, I guess we have more than one step. Our last step to get row echelon form is to divide out equation 3. So we'll divide by negative 2. That'll give us a 1 here, negative 1/2, minus 1/2. The other rows I haven't changed. And then we need to get rid of that 1 there. And so that's just going to be minus row 3 plus row 1. So we've got our identity there on the left, and then what happens on the right? If we take minus this guy plus row 1, so we will have 0, 1/2, and 1/2. Sorry about that. I need to change the silent hours on my phone to include this class as well. Okay, so we performed all of our operations. So this guy should be A inverse. And so by our work, our system of equations, we should have, let's go ahead and write it out just to check our inverse real quick. So we have our A inverse 0, 1/2, 1/2, 1 minus 1, 0, 1 minus 1/2, minus 1/2, times our A was 1, 0, 1, 1 minus 1, 1, 1, 1 minus 1, times xyz is going to be equal to 0, 1/2, 1/2, 1 minus 1, 0, 1 minus 1/2, minus 1/2, acting on 1, 3, 2. So, however much you trust your work, this was A inverse times A. We should be able to compute and check that the product of these two should give me the identity. So if we do first row times the first column, we'll get 0 plus 1/2 plus 1/2. So we'll get, actually, let's leave, I think that should be enough space. We'll have a 1 there. And then if I do first row times the second column, minus 1/2 plus 1/2 will give us a 0. This row times the last column will give us 0 plus 1/2 minus 1/2. So far so good. This row, first column, is going to give us 1 minus 1, gives us 0. This row, that column, gives us -1 times -1, gives us the 1. And then the last one gives us a 0. And then the last column, let's see, so this row times that one, 1 minus 1/2 minus 1/2. Bottom row, middle column, gives us 0, 1/2, -1/2. And then the last row, last column, gives us 1 minus 1/2 plus 1/2. So 1. Good. So we did our inverse correctly. We've got x, y, z. And now we need to perform this multiplication. So we will have 0, 3/2, and 2/2. So that'll give us 5/2. We will have 1 minus 3 plus 0. So -2. And then we've got 1 minus 3/2 minus 2/2. So 1 minus 5/2. So -3/2. We know, of course, the identity times this should give us the exact same thing. If you haven't checked that, do a basic calculation and show that the identity times anything will give us that anything back. And so this gives us our solution, our x, y, and z are equal to 5/2, -2, and -3/2, respectively. Any questions on that? Okay, so let's briefly touch base on transposes. We can talk more about transposes as they come up in the future. They are important in general for a lot of general theory of math, though I don't know how much we will actually get into stuff like that in this class. So it might not be terribly important. Really just simply understanding what they are. Pretty basic, and I think it's going to be easy enough for you to understand. So the transpose. So the transpose is just an operator. So if we have A, so again, this just means A is an m by n matrix. Capital M is the matrices. The lower indices tell us the dimensions of that matrix. Then we write an upper T called A transpose. Is a matrix. And we will say it's in now n by m matrices obtained by switching the rows and columns. So our A transpose, the ijth entry of A transpose is the jith entry of the original matrix. So that's the formal math, easily enough to just see an example to see how this works. Let's say A is a matrix, and let's do a non-square matrix. So let's do 2, minus 1, 0, minus 4, 7, and 35. Then A transpose, it's going to be, so the diagonals stay the same. So 1, 1 is going to be 1, 1. This one has position 1, 2, is now going to go to position 2, 1. So the minus 1 will be there. And so I made it a little too long. Should be wider now. And then the 0 is in 2, 1. It's going to go to 1, 2. Minus 4 is in position 2, 2. So if I flip the 2, 2, still in position 2, 2. Here I'm in position 3, 1. So it's going to go to 1, 3. And then the last one, 35, position 3, 2, going to go to position 2, 3. So that's all there is to it, to taking a transpose. So you can kind of notice it's kind of like, you don't just turn it sideways. It's kind of like flipping it and turning it sideways. So this row, the first column becomes the first row. Second column becomes the second row. Basic properties, and I'll leave these for you guys to check. They're all listed in the book, and I think the book might actually work through them. Encourage you guys to work through them on by yourselves, or at least try to justify it by yourself as to why these are true. The transpose is what's called a degree 2 operator, meaning that if I perform it twice, we get back to the original thing we started. So that one's easy enough to understand. The way transposes interact with products is that it flips the order. So it kind of anti-commutes, so to speak, with products. And then with scalar multiplication and addition, transposes work quite nicely. It doesn't affect any scalar multiplication, and it distributes consistently over addition. So a few definitions. So a matrix is symmetric if it's equal to its own transpose. We call the matrix skew symmetric if, when we take the transpose, we get the same matrix back, but negative. So maybe do an example. Let's take a look at why this terminology comes from. So if A transpose equals A, one thing we just saw in the previous example, when we are computing a transpose, the diagonal entries actually don't change, right? If I flip the position 1, 1, it'll go to position 1, 1. Position 2, 2 stays in position 2, 2. So one thing, if I have a transpose that is equal to itself, the matrix has to be square. Otherwise, the dimensions will get switched order. So we need a square matrix. And then what does A transpose equal A mean? So let's define A in terms of a symmetric matrix. So the diagonal entries are all going to be consistent. I guess they don't have to be the same. They can be different. They are commonly the same for a lot of the practice problems and the problems that we use this in. But essentially, the entries in opposite positions. So let's change one of these, actually. Let's change one of them to 1. Symmetric just means that whatever position it is in the row column has to be reflected over the diagonal, essentially. So if I have a 0 here, I have to have a 0 here. If I have a 3 here, I have to have a 3 here. If we have a -5 here, we'll have to have a -5 here. And so check that. If you check A transpose, what are you going to get? Diagonal entries are going to stay the same. And then if I have this position, well, this is in row 1, column 2, is going to go to column 1, row 2. So the 0 here will move here, and conversely, the 0 here will move up here. And so go through those if you'd like, but you should see that we get exactly the same matrix back. So symmetric really means symmetric across the diagonal. Skew symmetric, you can essentially think as the same thing, except one of the sides of the diagonal is negative. So let's do 1, 2, 3. Let's do 7, 8, and 11. Actually, we need to change this. One caveat. We'll see what happens, and we'll see why. So across the diagonal, it should be negative. However, skew symmetric matrices have the important property that the diagonal entries need to be 0. Since the diagonal matrices or the diagonal entries do not change when we take the transpose, if I compute B transpose, and if I want to get a negative of the matrix we just had, then that means the entries along the diagonal need to be negative of themselves, meaning they would be forced to be 0. So this one won't quite work because what's going to happen, B transpose is going to give us a 1, 2, 3 on the diagonal here. This -7 is going to come up here. The -8 is going to switch with the +8, and the -11 is going to switch with the +11 as well. But we didn't satisfy our skew symmetric, since B transpose is not equal to -B, because the diagonals should be negative. So really what we need would be a matrix with zeros. And so now when we compute the transpose, the zeros will stay the same, and the negatives will switch place with the positive numbers. And now we have the property that the transpose, I can obtain this transpose by simply multiplying all the numbers in C by a -1. Okay, so properties of inverses. Let's talk about those real quick. Namely, if I take an inverse twice, we'll get back to the original matrix. So the inverse operation is another degree 2 operation. The inverse plays nicely with the transpose. Namely that if I take a matrix and compute its transpose and then compute the inverse, it'd be the same as computing the inverse first and then computing the transpose. So both of those play nicely well together. Inverse has similar properties as the transpose in terms of how it affects multiplication. So if I have a product of two matrices and then try to take the inverse, it's going to be, whoops, I wrote that backwards. You have to flip the order. So it's going to be B inverse times A inverse. And then lastly, with scalar multiplication, our inverse is multiplicative inverse. So if I take a scalar multiple of a matrix, we actually have to invert that scalar multiple. So this is where it's going to be different than the transpose. And then I would also just say be careful with addition. Think of it in terms of general calculus. If I just had variables x plus y and then had that quantity to the -1, we can't simplify that, right? It is what it is. So this does not equal A inverse plus B inverse. So you cannot do this. Inverses don't distribute over addition. Any questions on those? I would say try to work out some of those examples on your own just to justify these inverses and properties on your own. Let's go ahead and move on to elementary matrices. So we've so far been performing a lot of row operations. We called them elementary operations, and then we realized they were row operations on matrices. And now essentially what we're going to do is formulate these row operations in terms of multiplying by matrices. So I mentioned yesterday that when we multiply matrices, you kind of want to think of it as one matrix acting on the other. And I'll explain a little bit more of that as we develop these elementary matrices. When we multiply two matrices, you can kind of think of the right matrix as fixed, and then the left matrix is going to transform the right. So the left matrix acting on it, multiplying from the left, is going to act on the right. And so in that regards, elementary matrices, so are n by n matrices. So they are square matrices. So they are in our set of n by n matrices that corresponds to elementary row operations. So let's list them all out and then we'll see some examples. The first one we have is switching a row and two rows. So I'll follow the book notation. There's a lot of different notation that we come up with for these matrices. The book uses P, and then it uses superscript I and J. So Pij corresponds to switching rows I and j. Be careful with the indices and our notation with indices. Of course, we're using I and j again, but these are two rows, row I and row j. Of course, we have commonly used ij to be row column. Let's actually call that point 1, or a transformation, or a matrix of type 1. Type 2, they use as E. I'm going to use T. I like to use I, J, K, and L for indices. And then like T and S are usually scalars, so that way it's a little more clear. This is just multiply row I by T. And then our third one, it's a little harder to notate, and I'm going to be a little more careful with it than the book. I'm going to actually write it out as like T times row I plus row J. So this is multiply row I by T, and then add to row J. So let's actually come up with these. The nice thing about these is they're fairly easy to come up with. You don't really have to memorize what these matrices are. And I wouldn't recommend doing it unless you have an impeccable memory, because the dimensions could change, the rows could change of what we're adding and multiplying and switching. So you don't need to memorize what the matrices are. Just know what they do. And then do that to the identity. So for example, let's say we have E12, and we want to know what this matrix is. And so let's say we're in 3 dimensions. E12 switches rows 1 and 2. Well, by the properties of the identity, it's going to give us back that exact matrix, right? It's going to give us the same thing. So how do I determine what this E12 is? Well, what is the identity? It's just the matrix with 1s on the diagonal and 0s elsewhere. So if I have E12 acting on it, well, what it's going to do is it's just going to switch rows 1 and 2. And I know that this had to have been E12. So we kind of think of these multiplying by matrices. Think of it as a transformation or as an operation, which we'll get into more in the coming weeks. So we can have an explicit matrix form of the transformation, or we can kind of know what the transformation does and then deduce the matrix form of that transformation via acting on the identity. Let's do another one. So let's say we are going to do, let's see, 2 times row 2 plus row 4. And let's say we are acting on the identity in degree 4, so the 4 by 4 matrix. Of course, it's going to give us back that exact matrix we want to deduce. And so if we have our operation acting on the identity, we want to take 2 times row 2, add it to row 4, and there we've came up with that matrix. So let's do a couple of examples, maybe in low dimensions, just to work it out. One thing I want to note, these elementary matrices acting on the left i.e. being multiplied on the left, correspond to row operations. So this isn't in the book, but I think it's an important concept to understand. Elementary matrices acting on the right, meaning if I multiply a matrix now with the elementary matrix on the right side, that corresponds to column operations. So far, when we've been creating these inverses, creating these reduced row echelon forms, we've only been working with rows. Trust me when I tell you we can actually do the same thing working with the columns. We can add and subtract the columns and get the same format, get the same reduced row echelon form, and we can actually do the same processes for getting inverses as well. And then that would correspond to column operations. So just as an example, if we switch rows 1 and 2, so we've got column, or excuse me, so we've got rows, so take the identity, switch the rows, so just a 2 by 2, and let's actually act on a 2 by 3. So let's say we've got 2 minus 1, 4, 7, minus 20, and 57. Did that in the wrong dimensions. Minus 20 and 57 here. Sorry, 2 by 3 is what I meant to draw. We should see that these two rows switch. We're switching rows 1 and 2 by this operator. And so let's compute it out real quick. When I take this row times this column, it'll just pick out that 4. This row times the middle column will pick out the 7, and then it'll pick out the 57. And then likewise now, when we move down to this bottom row, it's going to pick out the top value on each column. So first row, first column gives us that 2. Bottom row, middle column gives us a -1. Bottom row, last column gives us that -20. So we see how that flipped the 2 rows. Conversely, if we act on the right, sorry, 1, 0. And this is kind of the funny thing of how we can interpret these matrices. I can interpret this as the identity matrix flipped the rows, which means if I act on the left, it'll flip the rows of the matrix we're acting on. Whereas now we have this matrix on the right, so you can interpret this product as two ways. We can interpret it as this matrix acting on this matrix, on the right matrix, or since this is an elementary matrix obtained from the identity, we can kind of think as now this matrix, the left matrix being fixed, and then now this guy acting on the right. The product, the multiplication is still going to be the same, but I just want to illustrate this fact that now if we kind of think of this as acting on the right, it's going to flip the columns. So this would be a column operation, and it's obtained from the identity by flipping the columns. So what do we get when we multiply that out? We still do our multiplication as it's written. So when I have 2 times minus 1 times these guys times 0, 1, it's going to pick out that minus 1 in this first entry here. First row, second column. Well, now the ones on top, it's going to pick off that 2. And then we'll have just the minus 1 times 0. And then we can keep going. So minus 11 times 75, it's going to pick out that 75. Middle row, first column. We could do now the bottom row, first column, going to pick out the 35. And then the last 2 entries, middle row, second column, going to pick out negative 11. And then last row, last column, 102. Everyone see how that works? So play around with some more examples, especially with some of the other elementary row operations, to try to get a feel for how that's working. I want to go through a list of theorems and properties about elementary matrices. We don't have time to prove all of these, so just take these as facts and facts you can use and facts you might need to use for your problem solving, at least in terms of your understanding of how these things are going to operate. So, first theorem is that elementary matrices are invertible and their inverses are also elementary matrices. That should make pretty intuitive sense. If I have an elementary matrix that switches 2 rows, then if I switch those 2 rows back, it will undo that operation. In other words, doing that twice will be the identity. We'll get back to where we started. If I multiply a row by 2, I could then multiply that same row by a half, and we'd get back to where we started with. And again, all we're doing in each of those cases are multiplying a row by a constant. Those are both elementary matrices. Work out the same kind of condition. If I add a multiple of one row to another, I could then maybe add the negative multiple of that same row back to that row, which will undo that operation. So anytime I perform one operation and then undo it, that's like doing an inverse operation. That's kind of the intuition you should have for what an invertible matrix is. It's kind of undoing the operation of that first matrix. So we've got other theorems. If we have a matrix, some n by n matrix, and B is the reduced row echelon form of A, then B is equal to U times A, where U is a product of elementary matrices. So in other words, now these row operations that we've been doing, we've been kind of notating it, and I've been kind of writing out to the left of the matrix of like what operations I'm doing. You could actually now instead just write the matrix multiple that you're doing corresponding to that row operation. So for example, if you start with A and then your next step is to switch 2 rows, now I switch those 2 rows to get a new operation. And then you can add a scalar multiple, oops, E of say row 1, and then add it to row 2. So you can kind of keep track, and sorry, I forgot the switch there. And then you can kind of just keep going. Every time you're performing a row operation, you can add to the list the sequence of row operations you're doing by just simply multiplying by on the left by that corresponding matrix. Maybe we'll see an example of that. I want to get through more of these theorems and get into LU factorization, and then we'll see how much time we have to do examples. Of course, what this illustrates is that if we needed to find this U, then it's the same process we've done by finding reduced row echelon form, and similar to how we find the inverses of a matrix. So if you take a matrix A and then just add on the identity to the right, and then now perform your sequence of row operations, essentially what that does is, since you're performing these row operations now on this sort of a joined identity, what that's going to do is keep track of what the operations are doing to the identity. And then in the end, that right side of the matrix will give you that product of all of those operations. And so from this, we can conclude that a matrix A is invertible, so it has to be square, if and only if it is a product of elementary matrices. So the idea behind that is, again, if we take a matrix, how do we find the process, or how do we find an inverse for A? We write A, and then we adjoin an identity on the right, and then perform a sequence of elementary operations, which we can now phrase in terms of a product of elementary matrices. And then that resulting product that we are performing on the identity will give us that inverse on the right. And so the inverse we can show is a product of elementary matrices. And so, of course, if the inverse is a product of elementary matrices, then the inverse of the inverse gives us back the original matrix. And the inverse of a product of elementary matrices is then going to be a product of elementary matrices. Does that make sense? Little hand wavy. I don't want to get too rigorous with it. Let me try to draw it out in some sense. We have our A. We stick with the I here. And what we do is we go through a sequence where if A is invertible, when we find the reduced row echelon form of it, we will get the identity. Right? We'll just have ones along the diagonal. And then on the right, what we're going to end up with is U. And so if U is A inverse, and this is a product of elementary matrices, let's just use generic letters. Let's just call them like A1, E1 times E2 times however many steps we needed to put that into reduced row echelon form. Let's say up to EK. Then by our properties of inverses, A, to get back the original matrix, we just take the inverse of the inverses, or the inverse now of the product. And by our multiplication property, this says that A is now EK inverse. You do the product in reverse. With each of the inverses of the elementary matrices, but each of these are themselves elementary matrices. Because anytime I undo an elementary operation, we are again performing an elementary row operation. So, our last theorem is that A is invertible if and only if the reduced row echelon form of A doesn't have a row of zeros. This is what we call a full rank. The rank of A is full, which means that the rank of A for a square matrix A is equal to the number of rows. We'll be able to phrase this in terms of linear independence in the next week, once we introduce a little more abstract notation about vectors and linear transformations. But in some sense, this is kind of how you define rank in general, right? The rank of A, you can think of at the moment as the number of rows that a matrix will have that aren't zero. Okay, any questions? There is one thing to note, and I think it's an interesting mathematical concept that we've talked about, a lot of these invertible matrices, and we've shown how an invertible matrix has to be a square matrix. However, I can take a product of two matrices and get the inverse, even if those matrices aren't square. So this was an exercise in the book. I want to leave it to you guys to work out, since we do have to talk about LU factorization today. But let's say we have a matrix that isn't square. It looks kind of like the identity, but it's got some extra rows of zeros. You can show that A transpose times A is going to give us the identity. And that'll be a two-dimensional identity. So when I flip A, it'll be, right now it's a 3 by 2. And then A transpose is going to be a 2 by 3. So that A transpose A is going to give us the identity, but when we flip them, A times A transpose, it doesn't give us a three-dimensional identity. So this is a concept that we call just a partial inverse, or a left or a right inverse. So it's not fully invertible. However, we could say A is the right inverse of A transpose, meaning that if I multiply A on the right of A transpose, it'll give us the identity. So these have important properties as well. An interesting thing to note in the compute and to understand, and it does come up in higher math. If any of you guys have to take that, some of you physics majors might see it in differential geometry or something. Okay. So last topic for the day, we've only got about 20, 25 minutes, is going to be LU factorization. So this is going to be the last technique we have. This is another computational technique for solving systems of equations. And make sure you guys know this. So I will put a problem like this on the midterm tomorrow. It's not terribly complicated, and it is actually quicker, theoretically, than doing row operations. So it, on average, uses half as many operations as reduced row echelon form. So we've used our reduced row echelon form operations to solve or to simplify a system of equations to find answers much more quickly. So the L stands for a lower triangular matrix. It's going to have ones on the diagonal. The U stands for upper triangular. Not necessarily with ones on the diagonal. So you'll see what upper and lower triangular are. It's pretty easy to see by example. Essentially what we want to do is, let's give ourselves some space. Let me start a new page. Everyone caught up with notes? Fortunately, all these linear algebra examples, they take a lot of board space, a lot of paper. So example, let's see, find an LU factorization of, our matrix is 1, 2, 0, 2, 1, 3, 2, 1, and 2, 3, 4, 0. So in LU factorization, it's going to be, so it's a 3x4 matrix. So what we're going to do is have a 3x3 is going to be our L. So the L matrix, I think you always want to choose that one as square. So you're going to have ones on the diagonal. And what does lower triangular mean? It means on the lower side of that diagonal is where all the entries are. All the entries above the diagonal are 0. So we want to be able to write this matrix as a product of some matrix of this form times a matrix of an upper diagonal matrix. So the upper diagonal is going to have all of its matrix, all of its entries, non-zero entries, on the upper side of the triangle. And then below the diagonal, it's going to have all zeros. Did I miss a row? Hang on. We need that to be 3, A, B, C, D, E, F, G, H. I missed a row. We should have 2 zeros here. Wait, what did I do? I'm writing this as a 4x3, and then I think I've just used too many letters. Let me rewrite this, sorry. 1, 0, 0, x, 1, 0, yz, 1, times an a B, and a C, a D, an E, and then an F, G, H, I. So unfortunately, with the non-square matrix, the diagonal, we only have 3 zeros below that diagonal, but we can't have extra terms above it. And so what we are doing now is looking for this product. There's two ways to find an LU factorization. This method is called essentially brute force, where we simply wrote out what we want the factorization to be in some sort of generic form. And now we can solve each variable one at a time. It does go pretty quickly. Upper triangular, and lower triangular matrices, when you're taking the products, the nice thing about how they're designed is that the product is easy. So namely, like this first entry, I know that the first row times the first column is going to give us that A is 1. The first row times the second column gives us that B is 2. First row, third column, D is 0. And then G has to be 2. So we get those variables pretty easily. Just from essentially the first row. Then the second row, we will have to do a little bit more work. So we want to find X first. So if I do the middle row times the first column, we're just going to get X times A is equal to 1. So we have X times A equals 1. So we know that X is also equal to 1. So we can actually go ahead and fill that one in with a 1. And then perform the rest of the multiplication. So when we have the middle row times second column, it'll give us xb plus c is equal to 3. But we know x and we know b. So c is 1. Likewise, e, we will have d plus e. So middle row, third column, gives us d plus e is equal to 2. And our d was 0, so our e is 2. Et cetera, et cetera. Do you guys want me to finish those? Hopefully, I think everyone, you should have enough skills if you're in this class to finish those computations. It does seem a bit lengthy, but apparently it is quicker than row operations. Let's try to see how we can do this. There's one other way we can compute an LU factorization. And then we can use LU factorizations to compute solutions to a system of system of equations. And it gives us another method. It supposedly is quicker than finding inverses and finding row operations. But in smaller dimensions, especially 3x3s and these types of things, I think both methods are fairly equivalent. Let's take a look. So let's say we've got a matrix A, and let's choose 1, 2, 3, 2, 3, 1, and -2, 3, -2. So first step is to come up with an LU factorization. One point about LU factorization, it's essentially obtained by operations of type 2 or 3. So no switching rows. So if we just keep all the rows the same and then take scalar multiples and scalar multiples plus other rows, we can obtain an LU factorization. So the way it's going to work is if we start with our matrix A, we're essentially going to go about a similar process as row operations, but the only thing we need to do is obtain an upper triangular matrix. And then we want the corresponding matrix on the left to be a lower triangular. So as long as we perform our row operations correct, it'll work out. So for example, let's suppose we take -2 times row 1 and add it to row 2. Now, we don't want to change the matrix, or we don't want to change our expression, so we also need to undo that operation, meaning we should take 2 times row 1 and then add it back to row 2. And what we're going to want to do is keep track. We're going to perform this operation on our matrix, and then we're simply going to keep track of these guys on the left as our product. So what's going to happen is when we perform this operation, we'll have 1, 2, 3. -2 times row 1 is going to give us a 0, -1, and -5. And then what we have to undo that operation, so here, let's list out our steps. Really, it's A is equal to this product times A. These two operations you should check are inverses of each other. They undo each other. And so if we've performed this operation on A, the inverse operation we can obtain by performing this operation on the identity. And again, check, if I performed this matrix multiplication, we should get back to where we started. What's this one going to do? Well, the first row is going to keep all the top entries the same. The second row is now going to add 2 times the first row to this second row. So it'll undo and get us backwards. But notice now that we're getting closer to an upper triangular matrix on the right, and this matrix over here is a lower triangular matrix. So now what we want to do is keep going with row operations here. So what do we want to do? We want to 2 times row 1 plus row 3 and perform that on this matrix on the right, right? We're trying to get zeros in these three positions. To undo this operation, we would take minus 2 times row 1 and add it back to row 3. So again, these two matrices are inverses of each other. So I'm not changing the overall expression. If we performed both of those, they would undo each other. It would be the same as multiplying by the identity. And then we're going to take this guy and perform it on the right matrix. And then we're going to have this guy act on the left matrix. So when we simplify this, on the right, what are we left with? R1, 2, 3, R0, minus 1, 5, minus 5, and then our 0, and then I've got 2 times 4 plus 3 is 7, and then 2 times 3 is 6, minus 2 is 4. Let me think, did I do that right? Did I miss math? 2 times row 1. Do we have a 3 here? Yeah. Or did I miss a minus? Nope. Give me 1 second. Let me double check my arithmetic. I'm working it out different in my notes. So when we do 2 times row 1, we will have 2 times that. 2 times 2 is 4, plus 3 is 7. 2 times 6, 2 times 3 is 6, plus 2 is 4. What did I do in my notes? Is that where I did it wrong? Minus 5. Nope. I think that's right. Anyone see any mistakes? Okay, and then let's go ahead and perform this guy on here. So I wanted to bring up the point about column operations because it's a little easier to interpret this as a column operation. You could think of this, so this is an elementary matrix, right? Which is adding 2 times row 1 to row 2. Or you could think of now adjusting it by column. So here this says minus 2 plus row 3. Now we're changing the rows to columns. So this will be minus 2. It's going to be hard to interpret. Let's draw it out. So minus 2 row 1 plus row 3 is going to give us a minus 2 here. 0, 1, 1, 0, 0, 0, 1, 0. So this matrix acting on the right, how does this matrix obtained? It's obtained from the identity by taking negative 2 times column 3 and adding it to column 1. And then we can perform that same operation on this matrix here. So we'll get 1, 0, 0, 2, 1, 0, and then negative 2, 0, 1. Okay, and then so our last step, we need to get rid of the 2 and or get rid of the 7 here. So the easiest way might be to multiply a multiple of row 2 to get that 7. So we've got 1, 2, 3, 0, minus 1, minus 5, 0, 7, and 4. What do we want to do? We want to take 7 row 2 plus row 3. To undo that, we should take minus 7 times row 2 and then re-add it to row 3. And then that needs to act on our remaining matrix. So when we perform this guy, what are we left with? 1, 2, 3, 0. We take 7 times this guy. So that'll give us I'm sorry, this row is not going to change. A 0 here. And then we'll have 7 times negative 5 is negative 35 plus 4 is negative 31. And then let's go ahead and write this matrix out and perform that operation as well. So we had 1, 0, 0, and then 7 times row 2, negative 7 times row 2, plus row 3 on the identity will give us this matrix. And now you want to think of this guy acting on this matrix to the left. So this is our lower triangular we're developing. You see the right term is now our upper triangular. And how does this matrix act on the right? It is minus 7 times row 3 plus row 2. So if I take minus 7 times row 3 and add it to row 2 on that matrix, we obtain our factorization. Everyone follow that? So some quicker ways you can interpret it. Anytime we are adding a multiple of a row to another row, the way to undo that is to just subtract off that multiple of the same row from the other row. And you can kind of see how it ends up operating. It doesn't matter if we act on the right or the left. The operations, in some sense, undo each other. So if we kind of follow these matrices and how they developed, if we multiply 2 times the first row to the, negative 2 times the first row plus the second to get rid of that, we have to take positive 2 times the first row, add it to the second. Then we took positive 2 times the first row and added it to the third, which means on the matrix to the left, we take positive 2 times the first row, add it to the third, or negative 2 times the first row, add it to the third. And then likewise with our last step. Our last step, I took 7 times the second row, added it to the third. So we should take negative 7 times the second row and add it to the third. So it kind of doesn't matter how you interpret the multiplication. Because you're working with a lower triangular matrix, the positions you are working with, you're not going to affect any of the other entries on the matrix. So it's fairly quick to perform each of those operations once you get used to it. And so our last step would be to solve an equation. So if we had something like the original matrix A, so if we had 1, 2, 3, 2, 3, 1, and minus 2, 3, minus 2 times XYZ is equal to, let's say, 1, 2, 29, if you can come up with an LU factorization fairly quickly, which if you kind of see our steps, we only did it in like 3 steps. It was fairly quick once you get used to the computations. We can write this as an LU factorization. 1, 0, 0, 2, 1, 0, 2 minus 7, 1 times 1, 2, 3, 0 minus 1 minus 5, and 0, 0 minus 31 times our XYZ equals 1, 2, 29. And so to solve for this, we can essentially do it in steps. If we call this guy X, this one our U, this one our L, and this guy our B, we have well, L times U acting on X equals B. And if we call this guy Y, we have Ly equals B. And if we give Y some generic variables, Y1, Y2, and Y3, then now all we have to solve is this guy first. Which we can do fairly easily because of the lower triangular nature of this. Namely, the first equation is going to give us y1 equals 1. It's going to give us 2y1 plus y2 equals 2. And so 2 plus y2 equals 2. Y2 equals 0. And then our third equation gives us 2 times y1 minus 7 times y2 plus y3 equals 29. So y3 equals 27. And now our last step is to simply work with the upper triangular matrix. So we have y1, y2, and y3. I think I missed a minus sign somewhere. So we have our u times x equals y. So here's our u. Sorry, times x. This should be xyz. Times xyz equals what we just found, 1027. And now, by the nature of the matrix, these equations are fairly easy to work out. And I'll start with z. Unfortunately, the numbers don't work out. The numbers should work out much better on the exam and in all the homework problems. But hopefully the method is clear. Any questions on that? So we're out of time. We can start with this and talk about it a little bit tomorrow before the exam. So we will have, we'll try to use most of the time period for the exam if we can. And we'll try to make sure that all the computations on the exam aren't going to be too lengthy. Unfortunately, with a lot of these problems, there is just a lot of arithmetic